This video is an introduction to the exponential distribution. If x is a random variable that has exponential distribution with the parameter lambda, then the PDF of x evaluated at small x is given by lambda e to the negative lambda x for x greater than 0 and 0 otherwise. So when you have a variable with exponential distribution, think of that variable as some sort of waiting time. So maybe one is observing the arrivals of emails, and so x would be the waiting time till the next email. So then and then lambda here can be thought of as a rate parameter. That is, if we are looking at the example of observing arrivals of emails, then you can think of lambda as the number of emails arriving per minute or per unit of time. Now, to check that this is indeed a density function, we need to see that if we integrate this function from negative infinity to infinity, we get 1, which we do get. In this case, the integral from negative infinity to infinity of fx of x will reduce to the integral from 0 to infinity of lambda e to the negative lambda x dx. The reason is the density is 0 outside of the when x is negative, and this integral is a very easy integral to compute, and you can easily see that that's equal to 1. So this is indeed a density function. And here are 3 graphs of the density function for 3 different values of the parameter lambda. So if you look at the density function here, lambda e to the minus lambda x, lambda is a constant here, so e to the minus lambda x, we know it's a decreasing function like this. Okay, so that's the exponential. That's the PDF of the exponential distribution. Now let's look at the CDF. So the CDF is capital F of x. Well, that is the probability that x is less than or equal to small x. And in terms of the PDF, it is the integral from negative infinity to x of fx of t dt. And since the PDF is 0 when t is negative, this integral would be 0 whenever x is non-positive, and then this integral would be equal to the integral from 0 to x lambda e to the minus lambda t dt when x is positive, and one can easily calculate this integral to be 1 minus e to the minus lambda x. So essentially, for when x is positive, the CDF function evaluated at small x is 1 minus e to the minus lambda x. Now, the CDF, again, it's the probability that the variable x is less than or equal to small x. Now, if I look at the probability that x is greater than or equal to x, that's the same as 1 minus the probability that x is less than or equal to x. And the probability that x is less than or equal to x, that's exactly the CDF function evaluated at x. So this guy is equal to 1 minus e to the minus lambda x. If I plug that in here, subtract from 1, then I get e to the minus lambda x for any x greater than 0. So the probability that x is greater than or equal to x where x is an exponential, where x has exponential distribution with the parameter lambda, then this probability is e to the minus lambda x. Now the graph, here are the graphs of 3 CDF for 3 different values of lambda again. Okay, so now what we do is we want to look at the expectation or the mean and the variance of a variable that has exponential distribution with the parameter lambda. Now, if x has exponential distribution with parameter lambda, then if I take y to be lambda times x, then one can easily check that the y has exponential distribution with the parameter 1. So let's find the mean and variance of y first. So the mean of y, or the expected value of y, would be the integral from 0 to infinity of y times e to the minus y dy. Notice for y, the PDF, so for y, lambda is 1, so the PDF would be e to the minus y. So for y, the PDF is e to the minus y, and then you multiply that with y, and you should be integrating from negative infinity to infinity. But again, when y is negative, the PDF is 0, so that's why you go from 0 to infinity. And this integral can be computed by using integration by parts, and what you're going to get is 1. Now, to get the variance, we need to first find the expectation of y squared, which is the integral from 0 to infinity y squared e to the negative y dy. Again, e to the negative y is the PDF for y, and again you can calculate this integral by using integration by parts again, and what you're going to get is 2. So the variance of y would be the expected value of y squared minus the square of the expected value of y, and then if we subtract, we get 2 minus 1, which is 1. So if y has exponential distribution with parameter 1, then the mean of y is 1, and the variance of y is also 1. Now, basically x has exponential. If x has exponential distribution with parameter lambda, y is lambda x, then y has exponential distribution with parameter 1. Since we know that y has mean 1, the mean of y would be, since the mean of y is 1, so notice that x is equal to y divided by lambda, so the mean of y would be 1 over lambda, and also since x has variance 1, y would have variance lambda squared times 1, which, the variance of y, since x is equal to 1 over lambda times y, the variance of x would be 1 over lambda squared times the variance of y, which is 1. So you get the variance of x is 1 over lambda squared. So that's the mean and variance for the exponential distribution.